Let's begin the discussion in this module with an example from discrete random variables. So let's take a look at this specific example where we will graph a cumulative distribution function and also compute the probability mass function values. Suppose that the CDF of a random variable x is defined as follows. The way you read this is f of b equals 0 if b takes a value less than 0, 1 half if b lies between 0 and 1, 3/5 if b is between 1 and 2, 4/5 if b is between 2 and 3, 9/10 if b is between 3 and 4, and it's 1 the moment b becomes greater than or equal to 0. What it means is for any value beyond 4 all the way up to infinity, this cumulative distribution function will take a value of 1. So our goal, the question here, is to graph the CDF and compute the PDF and also graph the probability distribution function. PDF and PMF are often used interchangeably, so please don't be confused. They are often used interchangeably, the PMF and the PDF. So let's take a look at how you can develop the graph for the cumulative distribution function. So based on the information that is given to us, if the value of b is less than 0, your cumulative distribution function is 0, which means it stays at 0 all the way from negative infinity up until 0, where it increases by 1 half, which is this value right here, which is this bump that you are looking at, the 1 half. And then between 0 and 1 it stays at 1 half at this point right here, and between 1 and 2 it goes up 3/5. So essentially it goes up from 1 half to 3/5, whatever that difference is, and it stays steady between 1 and 2, and it goes up to 4/5 at exactly 2, and between 2 and 3 it stays steady at 4/5, and at 3 it goes up to 9/10, and at 4 it goes up to 1, and it stays 1 throughout all the way to positive infinity. So that is how you graph a cumulative distribution function. But then computing the probability mass function using this graphical approach is pretty straightforward as well, and now let's take a look at that. So the probability mass function that you're looking at here will essentially use the same scale. On the x-axis you have the real line. This is nothing but the real line. It extends all the way from positive infinity on the right hand side to negative infinity on the left hand side, and these are these masses of probabilities that we talked about in the previous module, where at 0 you see here that there is a bump of 0.5. That's the 0.5 that you see here. At 1 there is a difference between 3/5 minus 1 half, which happens to be 0.1. At 2 the difference is 4/5 minus 3/5, which is 1/5, which is 0.02, and so on and so on. And the way you know that this is a legitimate probability mass function is when you add all of these values, which is 0.5 plus 0.1 plus 0.2 plus 0.1 plus 0.1, the total happens to be 1, which tells you that this is a legitimate probability mass function. At this point, I want to bring your attention to the summary of random variables, both discrete and continuous, that we looked at in the last class or the last module, and I want you to pay attention to these things just so this difference is very clear for you. The f of x for a probability mass function is defined as probability that x takes exactly a value of k for all k in the range of this random variable x. The CDF is defined as the capital F of A, where you're trying to find the probability using this density function up until the point A, which means you want to sum all values of k up until point A. On the continuous random variable side, you have f of x being integrated between a and b. The way you compute that is as the probability that x lies between a and b. And the cumulative density function is, if you want to find the probability of this density function up until this point a, you integrate all the way from negative infinity up until a, f of x and dx. That will tell you the cumulative distribution function of that random variable. And I also want to bring your attention to the properties of the distribution function, so take a minute or take a few minutes to go over this part by yourself. And this will be critical because in the upcoming few minutes we will actually take a distribution function and prove that that distribution function satisfies these three properties, where if you take the limit of this distribution function to negative infinity, it is going to be 0. If you take the limit a tends to positive infinity, f of a, that is going to be equal to 1. And if you choose two values b and a, where b is greater than a, then the cumulative distribution function value up until point b is always greater than or equal to the cumulative distribution function value at the point a, which means the distribution function is always a non-decreasing function. Just like how we computed a distribution function from a density function, you can also find the density function from a distribution function. All you need to do is differentiate that density function with respect to y or x, whatever the random variable is, and you would know the density function. So if you have a distribution function, you can obtain the density function by differentiating it. Similarly, if we integrate a density function, we get the distribution function. So if you want to go from PDF to CDF, you integrate, and if you have a CDF and you want to find the probability density function, we take the CDF and differentiate it. So it's good to kind of remember these two things, which will come in very handy. Just like how we have some properties for a distribution function, we also have a couple of properties for a density function. Your f of y is always greater than or equal to 0 for all y in the range of y. And if you integrate the density function between negative infinity to positive infinity, the answer is always equal to 1. Now let's try to solve a problem based on a given density function. And density functions have different uses, and you can see here a practical example. The change in the depth of a river from one day to the next, measured in feet at a specific location, is a random variable with the following density function. And the density function f of y is given to be k if y is between -2 and +2, and it is 0 elsewhere. And the question here is, find the value of this variable k and then find the distribution function of the random variable y. To find the value of y, we can simply integrate the density function between the limits and equate it to 1, because only when we integrate a density function between its limits we get the value of 1. So we can use this technique to find an unknown variable, which is k in this case. So if we integrate this function k dy between -2 and +2 and equate it to 0, and in that way we can try to find the unknown value k. So this is a pretty straightforward integration problem. K is a constant. I can bring it outside. -2 to +2 dy, and the integration of dy is simply y between the limits -2 and +2. And when I substitute these values to integrate this definite integral, we get k times 2 plus 2 equals 1, or k equals to a value of 1 over 4. In other words, the density function can be written as f of y equals 1 over 4, which we just found out, if y is between -2 and +2 and the value is 0 elsewhere, which means it tends to look like this kind of the graph representation of this specific density function, where between -2 and +2 it is always taking the value of 1 over 4. So there's a continuous random variable, and we just found the density function by simply integrating. We took the original density function where we had k, which was an unknown value, and we equated that to 1 on the right hand side to show that this is a legitimate density function, and we found the value of k, which happened to be 1 over 4. Our next step is to find the distribution function using a given density function. To find a distribution function from a density function, if you remember, we had to integrate. So what we need to do is we pick a point x, not k. So let's pick a point x between -2 and +2 and integrate up until that point x to get a general expression or a general equation. So in this case, I want to take f of x and integrate that from -2 up until x. Okay. So you have 1/4 outside, which was a value of k. This 1/4 stays here, and now you have value of y with these limits -2 and x, and if I substitute that, I get x plus 2 divided by 4, or x over 4 plus half. So this is a cumulative distribution function, a general expression of the CDF. This is called a general expression that can be used to answer other types of questions as well. Now if you want to check if we get the density function back, we simply need to differentiate it just to make sure we got the right answer. So all you have to do is, if you differentiate this, so if you remember, always remember this, if you want to go from PDF to CDF, we integrate. If you want to go from CDF to PDF, we differentiate. And that's exactly what we want to do. If you want to check to make sure you got the right answer, is simply integrate this CDF and we get back 1/4 right away, since the differentiation of this thing is 1 over 4. Since 1/2 is a constant, that goes away. So d by dx of f of x is nothing but 1 over 4.